Everyone, it's my great pleasure to welcome to the Deep Learning Indaba Adji, Boussi, Dieng. The sound guy has fixed it, thank you. She has done amazing work. She's currently a PhD candidate at the University of Columbia, has done really amazing work in probabilistic modeling and methods of inference, a lot of interest in natural language processing. She has also recently joined us on the Indaba committee as one of the chairs of the Indaba Awards program. So you'll see her again later in the week. And she's going to give us this next 2 hours, a really interesting journey through one of the most interesting, at least for me, areas of machine learning right now on generative models. I'm really excited to get to learn from her and see how she presents. So please join me in welcoming Adji to the Indaba.
Thanks, Shakir, for the warm welcome. Thanks, everybody, for coming. I'll talk about, okay, something happened. I'll talk about deep generative models, like Shakir mentioned. And the setup that I came up with is, okay. So I'll start up with what we're working with, and then mention what the roadmap is for the lecture, and then we will go from there. What I'm hoping is that along the way, you will ask questions as they come so that it's more interactive, and I'll try to answer as much as I can. If I don't find a good answer, please blame it on the jet lag and not on me. So the setup is that we have a set of observations, x1 through xn, that follow independently and identically distributed a distribution PD of x, and we focus on one data point, say, and then posit a model over the data, that's P sub theta of x, and our goal is to learn those model parameters by trying to make this density P theta of x as close to the unknown density as possible. And we will see that that boils down to minimizing some sort of divergence between these two densities. And a divergence is simply a measure of discrepancy between two distributions that satisfy these two conditions, meaning that it has to be non-negative and it has to be zero when the two densities are equal. And there's, of course, many approaches to this setup and this problem, but I will focus on two approaches that are currently very used everywhere, that are variational autoencoders and generative adversarial networks. First part will be on variational autoencoders, and I'll cover some background on that, meaning we will revisit maximum likelihood, variational inference, variational EM, and the hope is that we can derive variational autoencoders from those simple principles. And then I'll move on to generative adversarial network, describing them, the generative process that they posit, and also the objective function. For both of them, I'll mention typical applications and some of their flaws and how people have tried to solve those problems. And then I'll finish with concluding remarks which are mainly what are current interesting lines of research when it comes to deep generative models. And I'll talk also about evaluation, which is very critical. Does this plan work for everyone? Great. So variational autoencoders. When I think about deep generative models, I think about the generative distribution, meaning how they posit a generative process for data. And I also think about what's the objective function that's used to fit the model parameters. So that's how I characterize a deep generative model. For VAEs, they posit a generative process that says sample a latent variable z from some distribution P of z called the prior, and then pass that through a neural network, a set of many layers of nonlinear layers, and then which is f theta of x here, parameterized by theta, and then you will take that output, add noise to it, and consider that to be your sample. What that means is that the implied generative distribution for a VAE is this integral, infinite mixture if z is continuous. So you're saying that I generate data by, like I said, generate from the prior and then pass that through the likelihood. Talk about some notation and some nomenclature. P of z is called the prior, and for VAEs, it's usually just a simple standard Gaussian or a uniform distribution, mainly Gaussian. And then you have P of X given Z, which is by abuse of notation called the likelihood, and it's typically Gaussian or a Bernoulli, because we deal with images most of the time, and they're either binary or you have non-binary images. And then you have the joint distribution, which is just the product of the prior and the likelihood. This joint distribution induces a posterior distribution over the latents. The posterior distribution is the conditional distribution of the latent variables given your data. And they're given by this formula called Bayes rule. I think you saw that yesterday. It's just the ratio between the joint and the marginal. The marginal is what I've called so far the generative distribution. So concretely, for a typical VAE, you have standard Gaussian prior, and then your likelihood, suppose you have non-binary images, will be a Gaussian, where the mean is the output of the neural net, the f theta of z, and then you add noise to that, meaning you take, for example, a vector sigma and a standard Gaussian noise and add the two together. This is some reparameterization for sampling from a Gaussian distribution. I made the assumption here that the variance is shared among all components and doesn't depend on the data point. That's a simplification. You can have, of course, a more complicated variance, say a full covariance. Before going to how VAEs are optimized, I'll go through a simple example illustrating maximum likelihood. So consider you have a set of data points, n, and they follow this simple model. That's Gaussian with variance 1. So the variance is fixed and shared between all of them, and they have mean theta. Now our goal is to learn theta through maximum likelihood. So what you'll typically do is use the definition, which is that you're trying to find theta such that you maximize the joint distribution of the data points. So that's what I noted, argmax over theta of p theta of x1, xn. And then because they are IID, you can rewrite this as argmax over the product of the marginal distributions. And then optimizing this is equivalent to just taking the logarithm of the joint, because log is log x has the same, because the logarithm has the same optimum as the original objective. And so log of a product is the sum of logs, so you end up with this sum I from 1 to n of log p theta xi. And then using the Gaussian assumption on the observations, you have negative 1/2 sum I from 1 to n xi minus theta square. Here?
You speak closer, so try to stop it.
Oh, you mean?
Yeah, so just bring the mic closer.
Closer?
Yeah.
Oh, closer works. Okay, thanks. Thank you. So the objective function turns out to be that negative sum of squares. And then for learning, you usually take your gradient of the objective function and set it to 0. When you take the gradient of this objective with respect to theta, you end up with an estimating equation that is sum of all your data points minus n, the number of data points, times the parameter is equal to 0. That's the equation that the optimal theta satisfies. And what you end up with is that your optimal parameter is this empirical mean. And so here we were able to tractably get a closed form for our estimates. For the estimate, an analytical form for the unknown parameter theta. And our hope is that we can do the same for the class of models that I just described. So I go through the same. I have my model, the one that I specified before, so n independent and identically distributed observations, and each factor is this integral. And I apply the maximum likelihood principle, so I say the optimal theta is the one that maximizes the likelihood, so product over the data points of p theta of xi, which is the distribution over each data point. And then I apply the log to that because remember the two solutions are equivalent. And you end up with summation over the data points of log of the integral. Now, I am at a roadblock here because I cannot continue like I did before. And the reason is that this integral is intractable. Even though P of z and P theta of x given z are Gaussians and we know their analytical forms, we cannot analytically get the expression for this integral. So we have to find a solution. And luckily for VAEs, there's a proxy objective for learning that is tractable, and we will drive that objective. So what you do is you take, I'm considering here one data point, xi. So you take log p theta xi and you write its definition. So we saw it was this integral over p theta xi given z, p of z, which is log integral of the joint. And what you do is use the important sampling trick. So you multiply and divide by some distribution. Let's call it q of z. And you end up with log p theta xi equals log of the expectation over this new distribution q of z of the ratio between the joint p theta xi z over q of z. And then from there, you can apply Jensen's inequality by using the fact that log is concave and you have log of this expectation, so you can switch the two, which gives you this lower bound, expectation over q, the new distribution of the log joint divided by the distribution q of z. And this bound is tractable. If we know q of z, we already know the joint because that was our model. We have power over what this model is, so we determined it. And so we can optimize this bound to learn the model parameters. And this bound is tight when this distribution q of z is equal to the true posterior, the conditional distribution of the latents given the data point. And so the question we have left to answer is what is this q of z distribution? There's a procedure that you can use to define q of z. It's called variational inference. In variational inference, you define your distribution q of z, you parameterize it. So you define a knob that I call here phi that you can vary to get to an optimal q of z. And the way you do that is this circle that I plotted here is my family of q phi of z. That's where the distribution q of z will live. And we want to find the optimal phi from this family that minimizes a specific distance. That distance is, remember the divergence that I mentioned at the beginning? This is another divergence, but now between our distribution, I haven't defined it yet, q phi of z and the true posterior. The way you do this is that you initialize your parameters phi and you march through this objective until you find the phi star that is closest to the true posterior. That's the distance that I had there. And you can say, okay, but this objective itself is also not tractable. Why is it not tractable? I'll pop up some questions from time to time. So why is this objective not tractable? I'm talking about the one that's KL, Q phi Z, and P theta Z given X. It's close, but it's not that yet. There's an unknown, yes, but it's not Z. It's which one is the unknown? The posterior, right? Yes. P theta Z given X is unknown. If it was known, we would be done already. But it's unknown. Fortunately, you can write, there's this relationship between your log P theta X and this KL divergence. And it's given by this first line in the bottom. Log P theta X is equal to something called the elbow plus the objective we are interested in. The elbow is defined as expectation under Q phi of z of the log joint minus log Q phi of z. And so what you can say from here, given theta is fixed, consider theta fixed for now, you have this relationship that because that is a constant now, optimizing the KL is equivalent to optimizing the elbow. More specifically, minimizing the KL is equivalent to maximizing the elbow. And the elbow is a tractable objective because there's no, all the distributions are known and we consider theta fixed for now. So we have an objective that's tractable for which we can get our Q of z distribution. So given that theta is not fixed, we can devise an algorithm that will allow us to learn both phi and theta. This algorithm goes as follows. You initialize your model parameters and you go through an iteration loop. And for each iteration, you find the optimal phi star, which we define as the one that maximizes the elbow. The elbow is the one that uses the model parameters theta from the previous iteration, because we already know those. And so you get your phi star, and then the next step within the same iteration is now to maximize the elbow with respect to the parameters theta. And the reason why we maximize the elbow with respect to theta is, remember, because maximum likelihood was intractable. So we said instead of optimizing the true likelihood, we maximize this lower bound if we know some distribution Q of z. Now at each iteration, we try to get that Q of z, which is Q phi star of z, and we optimize the elbow. And here I said you optimize the model parameters using SGD, but you can use any stochastic optimization algorithm. There are very complicated ones like Adam, Adagrad, all those are applicable here. You only need to pass them the gradient of the elbow. There's a problem with this algorithm. There are two problems. Who can tell me both of those problems or at least one? Questions will come up. The sampling procedure for which part? The sampling the mini batch? We can do that because we can say, pick a random, you have 1 through n, you can pick a random, say b random numbers from that and get that data, get those samples. So that is doable. Yes? Oh, tell me. Yes, that is one drawback. Great. So we have one left. That's true that here you define Q phi. Remember, I defined Q phi as this distribution for the data point. Now phi was the parameter that you acted upon to get to an optimal Q phi star. There's a phi for each data point. So if you have a very large data set, you will end up having these many parameters that you need to optimize. And so that's a problem. So what's the second one? It's in the algorithm. The first, yeah, it's in the algorithm. Go ahead. Yes, that we need to find the optimal phi at each iteration. That might take time, and so this algorithm in practice is not doable. You don't want to use this because of the two problems they identified, which is that you have too many, a parameter for each data point, which is not doable if you have very large data sets, which we typically do have in practice, and then there's this inner optimization procedure where you need to find the optimal phi. So we will mention solutions to each of these problems. The first one is amortized inference. What amortized inference does is that it tries to take care of the problem where you have a parameter for each data set. So that's what it takes care of. And what you do here is you explicitly condition on the data, x. So for each z, you condition on its x, and And so you end up having your variational, Q is called the variational distribution. I didn't mention that, but we will code it like that from now on. So you define your variational distribution as this product of all the data of Q phi Zi given Xi. Now, phi is, if you see, it doesn't depend on I, means that it's a shared set of parameters. And the way it's defined is it's usually the parameters of a neural network that takes Xi as input. So each of the factors, Q phi of Zi given Xi, is a Gaussian, say typically, or any other distribution, but it's a distribution whose parameters, say mu and theta, are defined as the output of a neural network. So you went from having a parameter for each data point to having just a global set of parameters to optimize over. That's what the neural net gives you. It gives you parameter sharing and efficient way to sample from this distribution. Was that clear? Can I read it? Yes, I said from the previous slide, we identified two problems. The first one was that you have a parameter for each data point, which might be a lot to optimize if you have one data point, one latent variable per data point. It might take too much time to converge. So what you do is, instead of defining your variational distribution, say, as a Gaussian mu I, sigma I, you now define it as a Gaussian mu phi of xi, sigma phi of xi. Now it depends on I through xi, but the parameters are shared between all i's, all data points. Yeah, and so instead of optimizing one distribution per data point, you optimize a neural network, which is a fixed set of parameters. Usually you typically sample from this using what is called reparameterization, which is easy for the Gaussian. Say you will just sample Zi from Q phi by using Z phi equals mean plus noise times standard deviation, which is what I wrote here. Of course, it becomes more complicated if you have distributions that are not directly amenable to this reparameterization, and people use reparameterization usually to reduce variance when optimizing the elbow, the objective that I mentioned before. But we will not go through all those details. Just consider that you have Q phi as a Gaussian, and you sample from it by taking the mean plus noise times standard deviation. And so now we have solved the first problem. The second one was that at each iteration, you have to find the optimal sets of parameters phi. Now, instead of doing that, at each iteration, we will just do one step of the elbow to find phi. Of course, that's not the optimal phi, but we will do away with it and just use this approximation. So this is how VAEs are learned typically. You just go initialize now your model parameters and your variational parameters, and you loop through iterations, and at each iteration, you sample mini batch of data points, and then you compute your elbow, which will depend now on both the model and the variational parameters, and you take gradient steps with respect to the model parameters and the variational parameters. So at the end, you will have both learned theta, and you have learned this neural network with parameters phi, and what it gives you is a posterior distribution over the latent variable. So you not only have parameter estimation, but you also have posterior inference, meaning that you can actually look at what a low dimensional representation of your data looks like. Is that okay so far? Great. And so let's look closely at what this elbow is. Elbow stands for evidence low bound, evidence being this log marginal, log p theta of x, and this is its definition. So you have expectation over the variational distribution q phi z given x of log p theta x given z, the same expectation over q of log prior minus log variational distribution. I just rewrote this. I just wrote the form of this elbow where I defined the log joint as log conditional plus log prior. And what it tells you is that if I have to maximize elbow with respect to theta, meaning that I will have to look at elbow and see only the part that depends on theta, it's like I'm doing maximum, like, go ahead. This one. Oh, here? Yes. So this is the form, this is the definition of the elbow. I want to maximize it with respect to both theta and phi. The part that depends on theta is only the first part. And so remember at the beginning we couldn't do maximum likelihood. We didn't have access to log p theta x because they depended on some integration of a z. Now, if you give me a z, and that z is coming from sampling from q5 z given x, I fix that z, you have now a well-defined density, the p theta x given z. Remember that Gaussian using neural net as a mean and sigma as variance. Now you have that available. So it's like you're doing maximum likelihood, even though it's not exactly maximum likelihood. So that's what maximizing elbow with respect to theta does. Now, maximizing it with respect to phi is basically, as we saw, is minimizing this divergence between Q phi and the true posterior, because we saw that there's this relationship between this KL, the elbow, and the log marginal, which doesn't depend on phi. And another way of looking at this maximization of elbow with respect to phi is to see that you can actually rewrite the elbow as expectation over Q of the log joint plus the entropy of Q. So the first term, when you maximize it with respect to Q, with respect to Q phi, is trying to find Q phi such that you can fit the data very well. And the second, I put it in the map estimate. And the second one is saying, don't just learn a point mass for Q phi, but try to make it have some spread. So that's why you also maximize the entropy. Now, those are not the only two forms of the elbow. The elbow has many forms, and depending on what question you are asking, you might want to prefer writing it in one way or the other. For example, the entropy regularization one that I just mentioned is useful in looking at what the elbow is doing when it comes to maximizing the parameters, optimizing the parameters of the variation distribution. You also have the elbow as the scale regularization form, which is to just rewrite that as expectation of a log conditional instead of joint. And what's left turns out to be the KL between the variational distribution and the prior. So here you can also think of it as try to learn Q phi such that you can reconstruct the data, but also make it close to the prior, which is a constraint. And yet another form of the elbow is, that I think is interesting, is you can write it as a KL divergence itself, but a tractable KL divergence, meaning a KL divergence between something that is called a variational joint distribution and the joint model, P theta xz. The variational joint distribution, Q phi of zx, is defined as your variational distribution times the data distribution. The reason why I think the KL perspective, this divergence perspective is interesting is you can say, okay, so then instead of maximizing the elbow, which is here equivalent to minimizing this KL, is it possible to use another divergence still in the joint space? And what would that give you? One form of the elbow that's illuminating is the second one, the KL regularization one, which has been attributed to a problem that all VAEs, many VAEs run into, which is the problem known as posterior collapse. What it corresponds to is that you have learned a model that makes its posterior close to the prior. And that is a problem. Why is that a problem? Why is it a problem when the posterior is looking like the prior? Yes? It's not what? Yes, it's not capturing the data, right? Which defeats the purpose, that's right, which defeats the purpose of posterior inference. What is also, what does that do? Why is that bad? Excuse me? It does not learn? That's close. Hmm? From, no. Because you still have, you're going from X. Remember, we defined Q phi Z given X as a neural network that takes X and then outputs Z. It cannot be identity, you know why? Because the dimensions are different. It could have been identity, that is true. If you had dimension of latence equal to, yeah, but that is not the case. We have a bottleneck. We have the dimension of Z usually very lower, way lower than the dimension of the data. Go ahead. Yes. But when, like he said, if the posterior is equal to the prior, then it means that it's not capturing the data. So that wouldn't be the case. The problem, the other problem is that, remember I mentioned, which slide was that? That our bound, this bound, AQZ log of the ratio is tight when Q of Z is equal to the posterior. So if it's instead is the prior, we have a very loose bound, and we are further away from our desired objective, which is log p theta x. That's why it's also bad when you're optimizing VAE and you run into this posterior collapse problem. Does that make sense? Right. So the practical manifestation of posterior collapse is that early on during training, you have this second term. Remember, I could write the elbow. One of the forms of the elbow is the second form. And what happens in practice is that early on during training, the scale goes to 0, which tells you that what happens when the KL goes to 0? The KL is a divergence, and I defined the divergence at the beginning. What does that mean when the KL is 0? Yes, excellent. So it means that our Q phi is very bad, which we don't want. And like I said, this has an impact on your performance. Generalization performance as measured by log likelihood, because our Q phi is not tight. It's not the posterior. And we are not learning latents that are meaningful. So people have focused a lot on solving this problem for VAEs. I will recapitulate in one slide. That will be very hard, what people have to have done. And it boils down to basically looking into what I think of in terms of degrees of freedom. You have the variational approximation, it's a degree of freedom, meaning you as a researcher has control over that. There's the prior, you also have control over that because you've defined the model. There's the likelihood, you have control over that. There's the objective function, which is the elbow, you can change it. And there's the optimization procedure. So there's a bunch of literature on fixing posterior collapse by looking into each of these degrees of freedom. So devising a richer variational distribution is one way, and early works on that have been hierarchical variational models, normalizing flows, and more recently on implicit variational distributions. These works, the original motivation was not to solve posterior collapse. But if you have a richer variational distribution, then that's a potential remedy for this problem. Because remember that the consequence was that Q is not capturing anything out of the data, which is we don't want. The second set of research is by looking into devising better priors. And the one that I like a lot is this one by Sack and Welling, where they define the prior as the optimal base prior, and then devise an algorithm for learning VAEs with this. And there, the bottom line is that you define the prior not as a fixed standard Gaussian, but also as a distribution with parameters, and you tune those parameters. The third set of research, I shamelessly put mine there, is by changing the conditional distribution, the one defined as p theta of x given z. And what you do there is you can act on that so that you enforce a higher dependency between your latent variable and your data, so that the latents capture something out of the data. And what we did in the paper is just put some skip connections in the generative model, and it turns out that that's actually effective at alleviating the problem to some degree. You also have a lot of work on changing the elbow objective. The first one, which is actually the first paper that identified this problem, is by Bowman et al., where you look at the elbow and this version of the elbow, and you basically introduce a parameter here, lambda, that you set to 0 at the beginning, and you incrementally increase lambda during optimization. And at the end of the optimization, you should be having a value of lambda equals 1, such that at the end, you end up actually maximizing the right objective. But at the beginning, you set lambda to 0, and increasingly augment lambda to 1. That's also sometimes very effective. And another line of work along that same procedure is the one on the beta VAE, where you set lambda and you fix it throughout training. And it turns out that actually does more than just avoid KL collapse. It gives you latent variables that might be disentangled depending on how you choose that parameter lambda. There's also work on using regularization on the elbow, on top of the elbow. Those are the info VAE type of work, where you introduce regularization that depends on the mutual information between the latents and the observation. Is everything okay so far? Did I lose anyone? Okay. And then other types of regularizer would be take out this scale divergence that's causing a problem and replace it with an adversarial, like a discriminator. And optimize the discriminator instead. And finally, yet another set of solution is by changing the optimization procedure itself. So instead of using the one that I mentioned earlier, where you take gradient step of the elbow with respect to both phi and theta, you simply, you still optimize the elbow, but you, for example, take multiple steps when optimizing phi, the variational distribution, as opposed to when optimizing theta. So that's, for example, what they use in the lagging inference networks paper, and which is very recent, and there are many works on that direction. Any questions so far on the material? Go ahead.
So, my question is, if you have these richer variational approximations, solve the posterior collapse, wouldn't they also, for example, data is like, if you have like image data with different classes, is it not possible for these models to also focus on a particular kind of data, something similar to mode collapse? So how do they
Sorry, what did you say?
Like, for example, these models try to solve the challenge of posterior collapse.
The original motivation was how can we do better approximate inference in variational autoencoders.
But yeah, but in a way, it kind of like gives some intuitions about how to remedy this posterior collapse.
Right.
Yeah, so my question now is, if we're using this for that case, doesn't it also affect, move to the cases where you're now having a mode collapse, like your model is now focusing on a particular mode?
That's a problem, but not for variational autoencoders. The mode collapse problem, I will discuss it later when I discuss GANs, is when your learned generative distribution p theta of x focuses only on certain modes of the data, like you said. For variational autoencoders, that problem doesn't happen And the reason is because they optimizing likelihood, it tends to put mass a little bit everywhere. So you don't run into that problem of dropping modes for variational autoencoders. I'll discuss that problem when I'll discuss GANs. But yeah, that's a good question. Yes.
Also, there was a statement as regards posterior collapse now. Now we are further away from the desired results, right?
Excuse me, can you repeat?
When posterior collapse occurs, we are further away from the desired results.
Mm-hmm.
So how come, since it's not learning from the data,
How?
how come are we moving away from the desired results since it's not learning from the data? Or am I missing something?
You are learning a bad generative model because you are not. Basically, it's like replacing. Where did I put it here? It's replacing this proposal Q of Z with the prior. So you end up having an objective that's very far away from your true maximum likelihood objective. And you cannot learn good theta for that. If I have a tighter bound that's closer to what I truly want to optimize, I'll get better performance than if you choose the prior as the proposal. Yeah. It's from basically in the VAE generator, you usually take Z. Remember, you have multiple layers, right? Z goes through the first layer, and all the subsequent layers, they do the compositional thing where you just take from the previous layer. If you're adding skip connections, you add the connection from Z to every layer, including the latest layer, the final one. The hope is that when you do that, you're forcing X to take into account your latent variable, and that has an effect on the encoder itself. Because there's a relationship between the mutual information XZ in the model and the mutual information XZ in the variational joint defined by the encoder. Does that make sense? Yeah. In general, if you impose, that's why these InfoVA works well. If you impose some sort of constraint that maximizes the mutual information between data and latent variable, then that's a good thing. You want to maximize that dependence. Because then your latents capture what the data, they capture the data. Yeah. Any more questions? Good. So I'll talk about applications now.
If you change the dimension of your of the latent in your decoder, would you add Z to the first few components, or because it's generally if you're generating images, you want to have a model that grows as you go forward.
Oh wait, say that again.
So if you're changing dimension,
The dimension of Z?
Dimensions of the width of the layer in the decoder.
Okay, the dimension of the layer of the decoder.
Yes.
Meaning the number of units in the decoder.
Yes.
Okay.
Could you just add the skip connection and add the Z to the first few components of...
All of them. All of the layers. All of the layers. You condition on Z on every layer. Meaning if one layer was computed as, say, hyperbolic tangents of W for that layer times output of the previous layer, let's call it H, plus some bias, you will have to add, it will become tan H of W for that layer, the output from the previous layer, plus another weight matrix, call it Q for that layer, times Z.
Okay, so there's a matrix, okay.
Yeah.
Okay. Fine.
Okay, on. Any more questions? Great. So I will discuss applications now. The one family of applications for VAE that I think is very useful is in chemistry. There's been a lot of recent work on using variational autoencoders to generate molecules. Sorry. To generate molecules. I don't know much about chemistry to determine whether this output is good or not, but this is from a recent paper from Ryan Adams' group where they basically generate a bunch of molecules from a VAE on zinc data of components containing zinc. I cannot interpret it because I don't know about chemistry. If there's anyone that knows about chemistry, you'll be able to know whether these are actually realistic samples or not. Bottom line is that you can use variational autoencoders to do this, and this might have potential use in automatic drug discovery. Another set of applications is in vision. There's a lot of applications there, one of them being denoising, meaning you put some noise on the image and you're trying to reconstruct the denoised version of your image. And the nice thing there is depending on how you noise your data, you can have different applications. For example, if I want to do image completion, my noising will be to just put a patch on some area in the image and try to reconstruct that. Here, what I'm showing here is just some random noise put on MNIST digits. But yeah, you can think about different ways, different forms of noise that will lead to different applications. Another one that I like is in text modeling. In general, latent variable models have been having trouble in text applications. And I think a lot of it has to do with this posterior collapse problem that I mentioned. But there's been an area where they have been very successful, which is in topic modeling. There, what people do is you just use, you parameterize the variational distribution over your topic proportions using this encoder. You sample from it, and you pass that through a decoder. The decoder is usually taken as linear. That takes a topic matrix B, deterministic, that you also learn, and dot product it with your topic proportion. Are people familiar with topic modeling? Yeah, so that's great. This is one potential application. And the reason why VAEs are very effective here is they allow you to do fast inference and evaluation for topic modeling. In the original LDA model, at evaluation time, at test time, once you've trained LDA, you will still need to run an optimization procedure to do evaluation. When you're using an inference network, when you're using a variational autoencoder, you wouldn't have to do that because once you have trained the encoder, it gives you a way of getting posterior distribution very easily. So you give me a document, I'll be able to get you, to give you the topic proportion for that document very quick, just by taking a pass through that neural network. No need to run another loop. That's why they have been used in topic modeling. So in this second part of the lecture, I'll talk about generative adversarial networks. This is shorter. I have shorter things to say for GANs, but after that, we'll move on to evaluation and research opportunities in this area. Any question on the VAE part? No questions? So remember, for variational autoencoders, we defined the generative distribution, P theta x, by sampling a latent variable from a prior distribution, and then passing that latent variable through a deep neural network. It's the same one that I call here, f theta of z, and then taking the output of the neural network and use that as the parameter of my distribution, the Gaussian, and you sample from that to get your sample. But here in GANs, what you do is you get rid of the final step where you add noise to the output of the neural network. Here you just sample Z from a prior, pass it through this deep neural network, and take the output as your sample. What this means is that the likelihood, what I defined as a likelihood, P theta x given Z, is not well defined. It's not a distribution, it's just a Dirac function. So it's a deterministic function from z to x. We will see why that might be limiting or that it might be helpful, actually. The reason why it's limiting is that you cannot do maximum likelihood anymore. We weren't able to do maximum likelihood for variational autoencoders, but we were able to find a tractable objective that mimics maximum likelihood, quote unquote. But here we cannot even have that objective because the likelihood is not defined. GANs have found a way of optimizing the parameters theta, not by maximum likelihood or by mimicking it, but by comparison. So what they do is you get a sample from your model. I described how you do that. And you compare that sample to the real data. And you do that in such that eventually the samples that you generate from your model look like the real data. So that's how they learn the model parameters. And effectively what that means is that you introduce a classifier called a discriminator in the GAN lingo. Let's call it d phi. Phi are the parameters of the classifier. They are not known. They need to be learned as well as theta. And you run through this minimax procedure that allows you to both optimize this classifier phi and optimize the model parameter theta. Bottom line is that this objective requires only samples from the data and samples from your model. So you don't need to specify a form for the likelihood, which is good for us because we don't have the likelihood available. And if you look closely at the objective, what it's doing is that with respect to phi, if you're maximizing this objective, you are making the data, the real data, be highly probable, and you are making the samples from your model less probable. That's the optimization with respect to phi. You can see that from the objective. When you are minimizing it with respect to theta, the first term doesn't matter. So this term wouldn't matter with respect to phi because it doesn't depend on phi. The second term is the only one that depends on phi. And when you're minimizing it with respect to theta, it means that you learn theta such that the discriminator puts high probability on samples from the generator. So that's a minimax procedure in the sense that the generator is trying to make the discriminator put high probability on its generated samples, but the discriminator is trying to make those samples less probable. Now, if you had to say, okay, what is the optimal classifier if I had to run this maximization to convergence? You can find that it's this ratio between the data distribution and the sum between data distribution and the model distribution, the generative distribution. Now, if I know that, then a possible learning algorithm, we will see why it's impractical, is to initialize my model parameters theta and then run through an iteration loop where at each iteration I will optimize phi, the classifier, to convergence using the previous set of parameters, theta t minus 1, and then I'll compute my objective with respect to theta, which is just the second term of the objective I showed previously, and you update your model parameters using SGD, or again, any form of stochastic optimization. Bottom line is that when you're doing that, you're using the optimal classifier. But the problem with this algorithm is that it's very costly. It's like the one that I showed for the variational autoencoder. You will need at each iteration to run this optimization through convergence, and it might take a long time. So the alternative that the GAN uses is to, instead of initializing just the model parameters and at each iteration finding the optimal classifier and optimizing theta using that classifier, it optimizes both theta and phi simultaneously. So you will initialize your model and classifier parameters, and then you run through a loop for each iteration you sample a mini batch of data, you compute your GAN objective, which now depends on both theta and the classifier parameters phi, and then you take, you update the classifier, and then you update the generator. The order here is important because we are doing a minimax, we are going through a minimax procedure. So if you look closely, the update for phi is using the previous set of parameters, whereas the update for theta is using the current updated phi value. So this is a proxy for what we wanted to do before, which is find the optimal classifier and update theta using that optimal classifier. Now, another thing that people do in practice is instead of using just one step of the classifier here, when updating phi, you run k steps. And k is usually 5, 3, and then before updating your model parameters. Any question on that? It turns out that we saw that for the variational autoencoder, maximizing the elbow is actually equivalent to minimizing KL over joint distributions. For the GAN, minimizing the objective with respect to theta when phi is the optimal discriminator. The optimal discriminator is the one that I mentioned here, is this ratio. This is the optimal discriminator. Now, when I plug that in the objective function for the GAN, you can show that it's actually this sum of two KLs, which is defined as the Jensen Shannon divergence between the data distribution and your model distribution. So it's like at every time, whenever we are optimizing theta, it boils down to minimizing some form of divergence. For GANs, it is this divergence. And there's one work, the FGAN paper, which tries to find other divergence alternatives to the Jensen-Shannon divergence. And one thing that I didn't say is exact maximum likelihood is also minimizing this KL divergence. Not the Jensen-Shannon, but the KL divergence, when your likelihood is well defined. So optimizing model parameters in most of machine learning boils down to minimizing a divergence. It's good to know which divergence is at play in every model you have. The procedure that the GAN uses, this minimax procedure, it usually leads to high sample quality. The reason is that unlike the VAE, it doesn't put mass everywhere. So it will try to capture modes of the data very well, but at the expense of missing some of the modes of the data. And effectively what that means more rigorously is that the support of your distribution P theta x is very low. And the way you see that in practice is that you have low sample diversity. What I mean by sample diversity is that when you generate from your model, you learn the GAN, you fix it, you generate from it, you'll tend to have repeated samples. Say if I trained the GAN using our pictures, it might focus on only me and people with breads and leave everyone else out just because it has collapsed to that mode. So that is a problem because actually GANs are used in some companies to augment data for data augmentation. And if you have a model that only can generate certain types of data, that's not something good to have. So we want sample diversity. One solution to low support problem is to maximize the entropy, because that's what it means. If you maximize the entropy, it will try to cover the whole mode of your distribution. The problem with GANs, what's the problem with GANs when it comes to the entropy? I think I already answered that in the slides. What's the problem here with the entropy? It's undefined, yes. The entropy is undefined because the likelihood is not defined. Remember, the entropy is defined like this. Is this negative expectation under your model distribution of the log generative distribution? And that is undefined because log p theta x is undefined. And so we cannot maximize the entropy. But there are people that have found fixes for this problem that can potentially solve the mode collapse problem. These are two sets of papers that I like because they're simple and they're intuitive. There's a paper called the vegan paper. There, what they do is they basically have this extra neural network. You know, GANs have like a generator, which is the f theta x, f theta z, that I mentioned before. This is the generator, but they also have the discriminator. Now, vegan introduces another neural network, a third one. And what that neural network does is that it takes the sample generated by the GAN and tries to output a latent variable z that's close to the latent variable that was used to produce the sample. So it's like a reconstructor network. And you learn the parameters of that network along with the parameters of your generator and the parameters of your discriminator. The reason being that you then will be able to somehow invert the generator so that it doesn't just focus on one mode. The second paper that I also like is the PAC-GAN paper. Go ahead. Yes. 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 And the one thing that I didn't mention is that now your discriminator is changed. The discriminator now takes the joint. It takes z along with x from, there's two joints. Remember, there was the quote-unquote variational joint and the model joint. The discriminator now takes the model joint and the variational joint. Here, the variational joint is defined by the reconstructor network and the data distribution. And yeah, that's how you learn the whole thing. The PAC-GAN paper uses the mechanism that they call packing, which is instead of just comparing one sample from the data to one generated sample from the generator, they will pack multiple samples from both the generator and the data. And then the reason they said this fixes mode collapse is then because you have a more appropriate estimation of your summary statistics from the data. And that helps in preventing mode collapse. These are two approaches that are very easy to implement, so I thought I would mention them. Now, there's another problem with GANs, is that they are very unstable. Why are they unstable? What can be, say, an explanation for instability? Is that we are comparing these two distributions, p theta x and pdx, and they might not share support at the beginning, which might make your divergence very, yeah, exactly. And so there's this trick that works very well in practice that's called instance noise. And what it consists in is that you will basically add noise to your real samples and to your generated samples before passing them to the discriminator. What that does is that it puts some spread on your samples and it allows somehow to find an overlapping support between the two distributions. There's the way they deal with the noise is that you can annihilate from some initial value, sigma naught, to 0, meaning that at the end you will be optimizing the original GAN objective, but you start with this noised mechanism for both the real data and the generated data to allow for overlapping support. And I recommend you read a blog post by Ferenc Huszár on how instance noise helps in stabilizing GAN training. Any question on that? no questions on GAN. Then I'll talk about applications. I think the domain where GANs are really, really successful is in vision. They have been used in any possible vision application. You can think of image generation. They can generate things like this. This is actually a slightly older paper. There are new ones like the big GAN or the style GAN that actually generate almost perfect samples. This is another paper called attention GAN. These are the samples that I'm showing are the class conditional from ImageNet, and you can see that they have high perceptual quality, which is what GANs are very good at. You can do image translation or generate any type of images. So I think they're very successful in vision, but you have problems adapting them to other domains, say for example in NLP or in domains where the data is discrete, and I will talk about that in the concluding remarks. Yes. Mm-hmm. Yes, that's a great question. And I didn't add a discussion to that because I have a paper coming out that's actually showing that GANs suffer from mode collapse, not only when the data has many modes, but also when the data is imbalanced. And what we showed was that if you take MNIST, which has only 10 modes, so it's very low number of modes, a GAN should be able to capture it. And it does when you take the original MNIST. But then when you make MNIST very imbalanced, then you can see that it drops many of the modes. And that's also an answer to your question that yes, they actually also have a problem when the data is imbalanced, which is a big problem when you consider data augmentation as an application, because a lot of these data sets, they're imbalanced. If you take, for example, let's say Celeb, this is a data set of human faces, and there are not many celebrities in that data set that have darker complexions. So if you train a GAN on Celeb and use it for data augmentation, you actually end up just generating images of light complexion faces. So that's a potential problem for data generation for GANs, is that this imbalance is something that needs to be taken care of. We identified the problem, and the solution, of course, is to fix the mode collapse problem. Because if mode collapse doesn't happen, then even if there's a mode of your data that has few observations, then it can also capture it, meaning that you'll also be able to generate from that mode. So fixing mode collapse for GANs is very important because of that type of application. Yeah. You mean the solution? You can think of them as imbalanced as well. You can think of the outliers as one that you don't observe too much from, and then it boils down to that same problem. Yeah. Yeah. Yeah, connect. Take this.
Yeah. So my question is about conditional GANs, where the distributions are conditioned on labels of the data set. Does it help with modal collapse?
Does it what?
Does it help with mode collapse for GANs?
It's the same issue, independently from whether you condition on labels or not. Conditional GANs also, they also have that problem. So it's not just because you're not conditioning on an input. Yeah. Is there a question on that? I'll talk about some research areas in this domain, and it's a very active area of research. For example, in VAEs, people have been looking at how to improve sample quality. Remember, one takeaway from this is that GANs are very good at generating samples that have very high quality, more than VAEs. And so, because inherently the objective that they minimize is what makes that happen. In VAEs, you have this likelihood proxy that somehow ends up producing samples that are of lower quality than a typical GAN. And that happens every time. And so there's research on how to make VAEs generate samples of higher quality. There's also research on how to improve posterior inference in VAEs. Remember, I mentioned this problem of latent variable collapse, which makes your approximate posterior Q phi of Z given X less expressive. So there's interest in having richer variational distributions beyond, say, normalizing flows, beyond hierarchical variational models. And one area that's been very exciting and interesting to people is in implicit variational distributions, where you make the same, remember, implicit distributions are the one where the likelihood is not defined. So here for a variational model, it will be, you only define it through sampling. Say, your variational distribution is, you generate a sample from your variational distribution, but by taking noise and then passing it through a neural net and consider that to be your sample. So the likelihood of the log density is undefined, but you have still an approximate posterior. So how can you do variational inference in that setting? How can you learn VAEs with that type of variational distribution? So that's an active area of research. There's also, remember when I mentioned VAE at the beginning, I said that they're trying to do maximum likelihood, but they cannot because the objective is intractable. So they have to use this proxy objective. Now the question is, how can you effectively do maximum likelihood in this type of model? For GANs, the main problem is mode collapse. So that's still ongoing. People have been looking at how to fix them. Entropy regularization is, of course, a natural solution, but the entropy is not available. And another aspect of research for GANs is, say, how can you do like VAEs, meaning instead of just learning the model parameters, how can you also learn a distribution that's meaningful over the latent variable? There's been work so a couple of years ago on combining variational autoencoders and GANs. And what you do is you add an encoder instead of just having the prior, and you do the procedure that I mentioned where you pass an input to the discriminator by concatenating a real sample with a latent variable from the encoder on one hand, and on the other hand, passing a sample from the prior concatenated with a sample from the generator. And you learn both all of them, the generator, the discriminator, and the encoder by following the usual minimax procedure. And so there's that, fixing mode collapse. There's better latent representation using GANs. And there's also this problem, the fact that the likelihood is not defined for GANs makes it impossible to have access to any measure that depends on the likelihood. So things like entropy are unavailable, log likelihood is unavailable, and the reason why that is bad is then because you cannot then evaluate GANs as density estimators. You cannot evaluate them in terms of how they generalize to new data. A typical measure for generalization to new data for density estimators is predictive log likelihood, meaning I will give you a new data X star, and you have to tell me how likely that is under your model. Usually what people do is importance sampling, the same procedure I use for VAE. So you introduce this proposal R of Z, you do the trick log, integral, multiply, divide by that proposal, and you end up with this objective. You end up with this form, and you can approximate it by Monte Carlo. The problem with GANs is that you cannot use this measure. to measure how they generalize, because p theta x given z, again, is not defined. So you cannot use log likelihood. So at the moment, there's no way to measure log likelihood for GANs. And there's been proposal to approximate this log likelihood by waiting at test time, at evaluation time, and then introducing a distribution on top of the generator and approximating the likelihood using kernel density estimates in unyield importance sampling. Of course, those are not, they can give you an idea of what the log likelihood is, but there's a lot of issues on, say, using kernel density estimates to approximate log likelihood, especially in high dimension. So there's still open problem in how do you measure log likelihood in GANs in a principled way. And I mentioned that for GANs, it's very difficult to use them on discrete output settings. For example, NLP, when your data is discrete. And the reason is, why is that the case? Why is it hard to use discrete data for GANs? Same. Okay, the likelihood is not defined, but we saw that for GANs, they don't use the likelihood. They have this minimax procedure that only requires samples from your model and from the data. Hello? Yes?
You have to have some mechanism to get back to one of your discrete points so if you end up with something in your embedding space,
right.
How do you get back to a real embedded vector that corresponds to something that...
What do you mean by that? You mean that is a problem?
Yeah.
But even if it was a continuous latent, we didn't have a mechanism for going back to the latent. We just picked the latent from prior, pass it through the generator, and take that as a sample, and say that's how we sample from the generator. For discrete outputs, why is that a problem? Huh? Can you take the mic?
I suppose the question is it because you use stochastic gradient descent in your optimization?
Right. Yeah, exactly. And so you are breaking back propagation when you sample, when you define a discrete sampling procedure. That's exactly the answer. And the way people have been going around that is using policy gradients or using gumbo approximations. But all those are, approximations. And ultimately, we would want to find a better way of dealing with discrete outputs. So that's an open area. And yeah, so it's a very exciting area of research. If there's no question, I'll talk about evaluation. No questions. Great. One big problem in generative models in general, not just for GANs and VAEs, is evaluation. How can you evaluate generation? For GANs, we saw that there's actually a further problem, is that you cannot evaluate how they generalize to new data because you don't have access to the likelihood. And that has restricted GANs to domains where you can use, say, perceptual quality measures to assess whether you're learning well or not. The reason why evaluation is important is because it tells you, okay, there's this generalization thing, but even when you're learning your model, if you have access to, say, log likelihood, then you can just output it from now and then to see whether your model is still learning or not. In the GAN literature right now, people measure progress during optimization by, say, of course, you output some statistics from the discriminator in the generator, but also you just look at the generated samples. If they look good, then you stop. If they still don't look good, then you continue, assuming that it won't diverge because we saw there were instabilities. So it's very fundamental to be able to have access to principled measures such as log likelihood, because it will help you tracking whether your training is being done right, generalization, looking at how two family of GANs compare, and you can apply to more domains because then you have other measures than just sample quality. So if you only have sample quality, you can only be restricted to domains where that is important, say in vision, which explains why GANs have been doing so well in vision, because you have a proxy for looking at how you're doing. You just look at the genetic samples. If they look good, then you say, okay, my GAN is doing well. But we don't want to do that. We want to have a principled quantitative measure for tracking training, but also measuring generalization and comparing different model families. Now, there's an area where there's nothing right now, is sample diversity. In GANs, you know, when you have, right now in the literature, what people do is you have these data sets, some of the data sets where you have the exact number of modes, say MNIST, you know that there are 10 modes. Stacked MNIST, you know that there are 1,000 modes, or depending on how you stack, but ultimately you know the number of modes. But for many data sets, you don't know the number of modes. If there was a data set of faces, which there are many of them, we don't know what the number of modes are. So we won't be able to measure the degree of collapse for GANs. And so currently in the literature, there's no measure that I know of that does this. So if you liked this lecture and you want to do research in this domain, I encourage you to look into quantitative measures for evaluating generative models. Yes, go ahead.
Hey, just on that, I've had an idea and I just wanted to run it past you. So you've got a generator and a discriminator in a GAN.
Yeah.
And essentially, eventually the discriminator will actually learn the generator's tricks, and that's how it becomes really good. But what if you also separately trained a classifier that hasn't seen any of the generator's output, and then you test how good the generator is at fooling that, and that becomes some sort of objective metrics?
How does that relate to diversity? Or is it another measure that you're talking about?
It's just a measure of the quality of the output, since you can't use likelihood. It's essentially how good is the generator at fooling a classification model that hasn't seen its generated images before.
So you train, okay, you have a initial step where you do the usual GAN training, and then the second step is what? You fix the generator and you train the discriminator?
Yeah, so I mean, the idea is essentially you train a discriminator without access to any of the generator's output, and then
that's just a classifier.
Yes, but then you use that to actually assess how good the generator from your GAN is.
I see.
Yeah. So I just wanted to see your thoughts on that idea in terms of coming up with some sort of objective evaluation.
Right. The thing is, I'm not sure in which of the criteria it's trying to measure. You know, there's generalization measures, there's sample quality measures, there are diversity measures. Those are the three main ones that I can think of, and I cannot put the thing you mentioned in any of those categories. So I'm not sure. We can take it offline if you want.